See, the core of NLP research happening nowadays is in the deep networks, neural networks. Even though NLTK is predominantly used, or similar frameworks are used for text processing, in the healthcare industry, because that's where you have a lot of unstructured text available, and then you need to have a lot of chunking and tagging and segmentation and lemmatizing and stemmatizing. All those things need to be done, and hence they're used there. But if you're trying to find a solution, even for a healthcare or for a product company or any other place using text, almost the default answer is neural networks. Use deep networks to solve a problem, and then we'll talk about some of the solutions. So the first stepping point to run a neural network or a deep network is you need to convert words into numbers, because computers can actually do well with numbers. You can do additions and subtractions faster than processing text. So there are multiple ways of converting word into a vector, and one of the most common and the earliest way of using converting a word into a vector is called one-hot vectors. One-hot vector, in simple terminology, is, let's say if you have a Wikipedia as your entire corpus, and the size of the vocabulary could be, let's say, 100,000 words. That means even though you have 3 million articles, and that even if each article is 1,000 words, you talk about a billion words, the size of the vocabulary, the actual number of unique words is on maybe 100K. I don't know the numbers, but 100K. And if you have these 100K, you can arrange the words in, let's say, in an alphabetical order, and you have a vector created with all zeros, and the size of the vector is the size of, or the dimension of your vector is the dimension of your vocab. So if it's 100K words, so first create an empty vector with all zeros, which are 100,000 size long. And the first word, whatever is the first word in your vocab, let's say hard work, I think the H is missing. The first word is zebra, let's say. In that vector of all 100,000 zeros, the first zero, replace that with a 1. So you have 100,000 numbers in the vector. First number is 1, and the rest are all zeros. That is a vector that represents the word zebra. And one-hot vector is, the concept of one-hot is, you have a vector with all the numbers are zeros except one number, and that one number signifies the location of the word in the vocabulary. So if you have 100,000 words, the first word is represented with 100,000 zeros except the first number being 1, and the second word is represented by 100,000 numbers, everything being zeros except the second number is a 1. So that's called one-hot vector. That's one way. That's one of the ways many times people have used to create vectors. There's another way of creating vectors, and the reason why this is not preferred many times is, in a sentence, the word, where a word appears, also has a significance. Whereas in the one-hot vector method, what you're doing is you're just arranging all the words in an alphabetical order, or any order, even if it's a random order. The location significance is lost when you have one-hot vectors. So NLP researchers felt that when you convert a word into a vector and use that vector to make sense, the way you are representing a vector, it is losing its location significance. And hence came another way of creating a vector called co-occurrence vector. So in this approach, you will identify what word comes before and after this word, and that will have an impact on the vector, or the numbers, or how the vector is defined will have a, let me repeat. The words that appear before and after will have an impact on what the vector will be for this word. That's what is co-occurrence method. And let's take an example. Let's say your entire corpora is 3 sentences. I enjoy flying, I like NLP, I like deep learning. And you want to create vectors for the word I enjoy, I like, enjoy, deep learning, NLP, flying. These are the unique words in this corpora. And so this is the entire corpora, and these are the unique words. And you want to have a vector for each of this. In a one-hot vector method, what you would have done is, for I, if this is the entire corpora unique vocab, 1, 2, 3, 4, 5, 6, 7. There will be 7 zeros, except the first word will be a 1 for I. For like, one hot vector will be 7 zeros, except the second 0 will be replaced by a 1. And for enjoy, there will be 7 zeros, except the third 0 will be replaced by 1 in one hot vector method. But in co-occurrence matrix, we are trying to see how to define the vector for a word based on what are the words that precedes and follows it. So in the co-occurrence matrix, for how many times the word I appear right next to I, how many times the word like appear next to I, how many times the word enjoy appear right next to I, that you need to figure out. So let's start here. How many times I appears right next to I? None of the time. I appears only once. There's no sentence called which says I. How many times like appear right next to I? 2 times. So you put a number 2. How many times learning appears right next to I? 0. So you keep on, and for example, let's say, how many times like appear right next to like? 0. But how many times like appear next to deep, and then there's 1. So you keep on filling up this matrix, and at the end of it, for each of the word, you have a matrix. Now, you can normalize the number where instead of having numbers above 1, you can actually have fractions, but that's a normalizing technique which is not relevant for current discussion. But then now you have a new way of representing a word as a vector which actually captures the information about what words come before this word and what word come after, and potentially in the process capturing some essence of the sentence construction too. But there are lots of problems with this type of, you had a question?
Does that ever generalize to like a radius of 2 instead of a radius of 1?
Yes. So as I mentioned to you, you actually can normalize it to, instead of having, in this case we have only 1s and 2s. It could be even 10, 20, depending on the corpora. And then you can normalize it to less than 1, where you actually can take an average and divide all numbers with the same unique average number, and then bring it down to a fraction. You can do that too. And standard NLP method, any neural network vectors today are all fractions. It's never a single number. But I'm teaching this topic right now just to show the multiple ways you can vectorize a word, and each of the approach has its own problem. So in this case, for example, the problem with this is, let's say you have an addition to the corpora. You have a new sentence. So you have 3 sentences here, and the 4th sentence is, I want to go to the movie today. And then the entire matrix changes. So this is a very unwieldy approach of creating vectors. If you are sure that I have my standard corpora, which I don't think is going to change for the next 6 months or 1 year, maybe you can go for a co-occurrence matrix. Using co-occurrence matrix to create vectors, and it does give some results, but within 6 months of proposing of this approach a couple of years ago, I think it was taken off immediately because I think it's unwieldy, it's not practical. So let's talk about, with that information in the background, and then I'll talk about another way of converting word to vector, converting words into vectors in a minute. But let me introduce a different topic, RNNs. How many of you guys have heard of recurrent neural networks? Okay, good. So I think this is the sort of a stepping stone for deep networks or deep learning, where a neural network, let's say as a single model or an entity, which continuously takes inputs one by one and continuously gives an output one by one, and also maintains some sort of a history. It also maintains some sort of an awareness of what was the past words that it has read, and that will enrich its outputs. So if you're using this for a translation, and if you're given a sentence, I went to the movies today, let's say from English to French, after the third word or the fourth word, it still knows, let's say John went to the movies today. So it still knows that the first word was John, and hence if its gender is male. So if there is a word that comes which refers to, which has an impact of the gender in my translation, I should be aware that the subject is a male. So that type of awareness it keeps. So typically inputs are referred to as X and outputs are referred to as O. Sometimes it could be something else too, but let's for discussion today, I think let's say inputs are X and outputs are O, and you see an S there. The most important thing in any deep networks, or in this case RNN, or I'll talk about a different model, is called hidden state. So it's some sort of the multiple terms are used by different researchers, but now I think for the last 6 months or 1 year, people have consistently been using the term called hidden state. So you may want to remember just the hidden state. So the hidden state of a network, in this case RNN, is a vector which actually captures the history or past information about the various inputs it has read. So in this case, xt minus 1, xt and xt plus 1. So let's say at this time, it has already read two different inputs called xt minus 1 and xt. So the hidden state is constantly changing too. It's actually updating the hidden state based on these inputs. So by the time you reach xt minus 1, you give a new input, even though it's processing this new input, but it also translates or processes it in the context of the updated hidden state, and the hidden state is influenced by the previous inputs. Actually, each input will have an impact on the hidden state, and hidden state gets transferred. So hidden state is one sort of information that the model remembers, which can be used for future. So that's what I want you to remember as a hidden state. This is, I think, a blog I was talking about. I think you should read this blog. You should read it multiple times. I've mentioned the link right at the bottom. If you can't see it, you should download the whole presentation, which is on my GitHub link, and then you can read that. This gentleman by name Andrei Karpathy, he's a Stanford graduate, I think a PhD guy. He's right now head of machine learning in Tesla, and then he's done lots and lots of research. He's taught a lot of courses in Stanford too. He has written a blog and developed a few models where he used an RNN to write a Shakespearean novel. How did he do it? He picked up all existing Shakespearean novels, fed those models into an RNN, and then after the training, the model is now intelligent enough to understand how Shakespeare writes. In other words, the model became Shakespeare, and using that model, he actually asked the model to write a new novel. Now, of course, there's not intricate plot in it, in the novel, but if you read the sentences, look at that. It actually identifies new types of actors or roles, people in it, and the sentences are almost grammatically correct. It is putting periods and commas, and these are all correct English words. And it actually creates roles like even the word duke. So it's creating a Vincento, and it says, okay, that's it, the guy is a duke. And then you actually talk about lords, and you have second lord and third lord, and you actually have a clown. And then the way a clown talks, when you're talking to a lord, maybe you have to say a sir, and then putting a comma. This is, guys, I want you to take a second and realize, this is a computer writing the story. And of course, in our terminology, RNN, model writing a story. And it writes scarily similar to what Shakespeare would have written. Shakespeare is dead long time ago, right? Because that's what I know. Yeah, he's dead long time ago. He's not writing it anymore. But you can train an RNN model to write a story. And look at this. Even Instead of saying I will drink, it's just for I apostrophe and two L's. The model knows what type of language. Let me pick a couple of words which are very, very typical of Shakespeare and Hyde. I see a couple of, I think, spelling errors, and I see there's no meaning in the sentence. They are away, this misery is produced upon my soul, breaking and strongly should be buried. When I perish, the earth and thoughts of men. There's no meaning in the sentence. I get that. I get that. But it writes a word which are 4 alphabets and 3 alphabets and 7 alphabets long. It knows where to put a comma. At the end of the sentence, it knows where to put a period. How many words can there be in a sentence? Of course, Shakespeare actually writes long sentences. But he didn't write a sentence with 100 words in it. And then it actually creates actors, and it actually puts a colon after that. It's amazing. And this, I think, he arrived at with using a 3-layered RNN with 512 notes, and the input size, that is the amount of text, all the Shakespeare novels was 4.4 MB file. And I think he would have run it maybe, I think, 20, 30 times, because I think it's called epoch. Epoch is the number of times you feed the same text to the model, and the models can start doing it. So that's the, call it magic, call it beauty, call it scary. That's what your deep networks can do in NLP. There's so many applications of this, but I just wanted to throw it right there at the start before we even talk about NLP, deep NLP, because you can do really magical stuff. And I talked about within NLP there's a section called question answering. So I did an experiment, I think around 6 months ago, where I wanted to create an NLP model where I feed a story and then ask questions. So I picked if you guys have heard of this, there's a great Indian epic novel called Mahabharata. It's actually a massive story, and it's available for free download online. You can download it, and it's written in English text now. So I trained an NLP model, LSTM model, on this text, on this story, and then after the story, if I ask a question to the model actually will give an answer with 72% accuracy. And this, of course, is a 1-month assignment. I just did it over a few days. I think in 2015, towards the end of 2015, I think Microsoft published a similar paper, and Stanford also published a similar paper, where they had the comprehension, reading comprehension of models. The accuracy rates were 72% at the time. Now I think it's coming to almost 80-85% accuracy rates. Still not 100%. Current models actually, but there are a lot more deeper models and heavy models.
Does that have to do with how you ask a question and it was something that was discussed in the last 5 sentences versus 50 sentences versus 5,000 sentences, kind of a memory degradation effect?
I have a slide for that towards the last when I actually talk about question answering. But a quick thing, it knows from the entire text where to look for first. And again, the question is not a simple, straightforward question. Let's say weather. Today's Cupertino weather is 70 degrees centigrade. All that it has to do is just a pattern match. Cupertino, and then look for the data, and then get the data. But if the story is different, I think at the start I was mentioning a story. Sally went to the kitchen, John went there too, and Sally said a hi too. The model has to understand the whole story and say Sally is saying a hi to John. Because Sally is in the kitchen, John is in the kitchen, human being to human being, possibly she's saying hi. So the question answering in the NLP models is no more pattern matching. So let's say if you have a story, Obama was the president of the United States, and if I say who was Obama, it can just look at pattern matching and just say, oh, Obama was the president of the United States. No, if the information is spread across multiple sentences or even multiple passages, it has to pick up. Right now the research is able to pick up the passages, but it can read information in the last, I think, 50 to 100 words. Anything more than that is becoming a problem. So the first step for question answering is the model has to figure out where do I look for the answer? The answer should be within the confines of 50 to 100 words. And then it understands the 100 words and then gives an answer. If the answer is spread across, let's say, 1,000 words, it has difficulty right now because I think it cannot remember. RNNs cannot remember, see, xt minus 1. So xt plus 1, xt plus 2, xt plus 3, let's say xt plus 1,000. By the time it becomes 1,000, the hidden state cannot capture information about x1 or x2 or x3. And that's a big problem. Even though this problem is solved using in LSTMs, it's called, the problem is called exploding gradients or diminishing gradients, and I don't know whether we'll have time to talk about that, but that's a topic. But anyway, actually that's a good segue. So RNNs, when people start using NLP models for RNNs being used for NLP solutions, they figured out if you have a long text, after some time the text, the model cannot remember or comprehend the text enough. If it's something like I said, 50 to 100 words, I think it can figure out. And the reason for that is, every time you update, you give a new input to the model, it understands what the new input is, compares it against the correct output, what's supposed to be the output, and it updates the hidden state. Hidden state is nothing but a big matrix. It's just a number. It's a massive number. It could be 50 by 50 size matrix, and each number could be 0.532786232, and you have such 50 times 50 numbers in a matrix. That's your hidden state. And every time you give an input, ask the model to make a prediction, and then whatever it predicts, you say, no, that's the correct prediction or that's a wrong prediction. It goes back and updates its weights. And these numbers are changing slowly. And the numbers are either increasing or decreasing, becomes negative or positive, all of these things. But the more the number of inputs you're giving, as I mentioned, xt plus 1 versus xt plus 1,000, by the time you give the 1,000th word, it does not have enough capacity to remember the first word. It can, provided the machines we are using nowadays have enough computing power. Let's say instead of having 12 GB or 24 GB, if you have maybe 1,000 GB memory, and if the GPUs can, or even TPUs can process, I don't know, a billion transactions in a second or a millisecond, maybe it can remember. But today's the technology, especially the hardware, is not allowing to remember that long. So, and because the matrix has a limitation of its own, and any changes in the numbers for the 1,000th word versus the first word, it becomes so minor, it just doesn't remember. It's like a human being. You teach a human being today, and a month later, at least for me, I would have forgotten all the stuff. And so my memory can only work for maybe a couple of days or maybe a couple of weeks, but not. Same is the case with RNN too. So to solve that problem, people invented a model called LSTM, long short-term memory. That's the name of the model. People just say LSTMs now, I think. In this is actually a variation of RNN. RNN has one layer, like it just takes an input, gives an output out, and then it has one hidden state. LSTMs, it's a very complicated explanation, but in simple terms, LSTM actually has 4 layers in it. It takes an input, does lots of processing. I can explain what the processing is. For lack of time and for the current discussion, and the most relevant information to remember in LSTM is, LSTM actually has one predominant output again, and that's called hidden state. So there are actually there's another thing called cell memory, is another data point that gets transferred from one timestamp to the other timestamp. That is, you have the first input as xt minus 1, and the next timestamp is xt, and the next timestamp is xt plus 1. Every time you're giving a new input, and the hidden state, it gets eventually updated. But it also has something called cell memory that is getting transferred. But the cell memory, which is actually CT, that is also eventually used to compute your hidden state. So at the end of each timestamp, the LSTM updates its hidden state, and hidden state is that vector that captures all the essential information that you want LSTM to work on. Let's say you have a sentence of 10 words, so you give in the first word, then give the second word, and give the third word, and the fourth word, fifth word, the 10th word. Once you're done with the 10th word, it knows the entire sentence. It knows the gender of the person. It knows who the subject is. It knows what information you're trying to capture, you're trying to say. Any other, I don't know whether it's any other information humanly possible, but lots of information a typical human being can capture is captured by LSTM in it. It is amazing. If you ask me, can you explain how? I don't know how. But lots of mathematics that happens in LSTM, lots of number crunching that's happening, but at the end of it, when you do, using the hidden state, when you do some transformation on the hidden state, it gives you dramatically accurate answers for your questions. And I'll talk about those, what the questions will be, what the answers are, how it is doing, I'll explain. But LSTM is a building block for your neural network, which solves the problem which RNN had. That is, if you have a long text of 1,000 words or 10,000 words, it solves the problem, but still not absolutely solving all the problem, but definitely solves better than RNN. And it's what it's doing is it's actually taking one word by word at every timestamp, assimilating the word, and then becoming smarter on that. And then when you ask a question, if you want to do some processing on it, it actually helps you. You have a question?
Yeah, so the X's at the bottom, those are our inputs, like each word, and then what are the H's at the top?
So the input is going in here, and these are the 4 different layers. You have we call it as 3 different gates. The forget gate, input gate, output gate, and there's some transformation happening. So the forget gate, what it does is it actually takes the input, does some sort of a nonlinear activation of that, and multiplies that with the cell memory, and then moves on to the next. And the same input is considered by the input gate, does a different types of transformation, and takes the previous hidden state and does a different mathematical equation, tan h, it's called tan h, and those 2 numbers are multiplied to each other and added to your cell memory. So cell memory from the previous cell got modified using the input in certain way, using forget gate, and the cell memory gets further modified by the input gates and the tan h gate, using the same inputs again, and the same input also goes towards the output gate, which has a different transformation, and that is further added to your cell memory using a tan h multiplication. Let's say just another number, let's say, and the cell memory gets now modified through these 2 different actions, and it gets transferred to the next timestamp. So the cell memory that's coming in gets modified twice and goes out, and in the whole process, it also updates your hidden state. Cell memory, even though is a number which goes from one cell to the other cell, it's not being used other than computing your hidden state. So for all practical purposes, if you have difficulty in understanding how LSTM works, I want you to think as LSTM takes an input, it updates your hidden state, and hidden state is what you want to take for any future processing in NLP. That's, I think, in very simple terms. But if this blog, I think you should read. This is another one of those famous blogs, like I don't know if you are into Bollywood movies, and there are Hollywood movies. Actually, there are a lot of classical movies, even over 10 years, 20 years. You still like the movie? This is one such blog. I think it was relevant 5 years ago, 2 years ago, and not 5 years ago. Sorry. 2 years ago, 1 year ago, I think it will be relevant for the next 2 or 3 years also, because it really explains what LSTM is. Because LSTM is a very complicated topic. And how do I say this? Even I took, I think I read this blog at least 10 times to understand what it is. But I think I was telling during the break also, what I'm teaching today in the 3.5 hours is what I took to learn in 9 months. So I don't know how much justice I can do in communicating all the NLP stuff, but I'm trying to pick and choose some of the really well. So all the links I'm providing in the presentation, I think you should go back and check those links too, because they're all interesting and useful information. So this blog explains LSTMs a lot more in detail, but the summary is you have the LSTM takes in word one by one and then updates the hidden state, and the hidden state is used for your computations further. Questions? Or did I confuse you more?
When you train, you make multiple passes?
Yes.
Right. So it's order independent, the final train network?
It's order dependent. It's order dependent because you actually input, let's say if you have a sentence of 10 words,
Sure.
you input the first word first and second word second and third and like
No,
that.
sure, but with respect to the corpus. So if I train a corpus on 1,000 news examples, 1,000 sports examples, 1,000 showbiz examples, will it think that Angelina Jolie is more important than Hurricane Harvey? Order dependent with respect.
Yes, it is. You're right. Or it's order dependent in the sense, I think I mentioned earlier also. Let's say you talk about Angelina Jolie movies, and then there's another person that comes with whose name is Jolie too, let's say towards the later part, and then you have more and more movies of that person showing up, and next time you ask the model who's Jolie, the model may say Jolie is the new person, you would have forgotten Angelina Jolie.
Okay, so we need to randomize the training sets, there's no distribution.
In NLP, in text, when you're giving information, within a single text, you need to keep the order, the sequence. Let's say if you're giving a story, you actually have to go the first word, second word, fourth word in the story itself in the sequence. But if you, let's say, the Shakespearean example I mentioned about, let's say you pick all the 20 novels of Shakespeare, then order doesn't matter. You can just random, and you can train in any order. But then it now understands the Shakespearean approach in a single time step. That is, it thinks all the 20 novels were written yesterday by Shakespeare, and then you're giving me those models, and hence I'm training on that. It does not know if the first novel written by Shakespeare and the last was 20 years gap. If you don't give the same sequence, it would not know. So to highlight this example, let's say you talk about hurricanes. So if you've been training a model on hurricanes, and then a few years ago you would have trained on Katrina, and then now of course you're training the model with information about Harvey, and if you ask a question about, without mentioning the name, if you just ask a question about hurricane, it will think that you're talking about Harvey and not Katrina anymore, because you have been giving more and more information of late about Harvey. So from that sense, the time sequence is important. It all depends upon what function you want the model to do eventually. If it's a one-time activity where the model is to be trained on Shakespearean novels and I want just to write a novel, yes. Or even going to the healthcare information. Let's say you have the healthcare corpora. You can pick the patients 2 years ago, 1 year ago, 5 years ago, 3 years ago. You can pick in any order and train the model. Now the model is trained on that knowledge which is provided, and then you can run the. So from that sense, it all depends on the sequence. Okay, the few building blocks I want to talk about in NLP, whether it's translation or question answering or summarization, people I think 2 years ago came out with this new model. Again, this is one of the 2015, I think, paper. You can refer to this paper to sequence learning with neural networks. This is the first building block after LSTM, so you can use multiple LSTMs. So if you want to, let's take an example of translation. You want to train an LSTM model to translate a sentence from language A to language B. It's called source language to target language. So you first give the input sentence in the source language one by one word. So let's say the input sequence is A, B, S. So A is the first word, B is the second word, C is the last word, and end of sentence is where you're telling the model, okay, I'm done with the sentence. And then the model will start outputting in this case, the translation is W, X, Y, Z, and then end of the sentence too. So this approach of giving the entire sequence of input first and then expect the entire sequence of output next is called a sequence to sequence model. So if you take a single LSTM, what the LSTM is doing here, you're giving A as an input, or if I use this picture, this is the same. In this picture, I don't want you guys confused. This is an LSTM shown 3 times. It's over a period of time, t minus 1, t, and t plus 1. Otherwise, it's just same. This is an LSTM. This is LSTM 2. So you give an input A at timestamp 1, and at timestamp 2, you give an input B. So for after A, it has a hidden state. And typically, for the first time when the LSTM is being initiated, you give a random hidden state, or you can just initiate the hidden state to 0, and then it starts modifying. So after A, it updates the hidden state. After B, it updates the hidden state. After C, it updates the hidden state. After EOS, end of sentence, it updates the hidden state. But end of state actually triggers the model that it's now my time to start outputting the translated sentence. So it actually starts translating one word by one word until it encounters end of statement. Now here is the magic. It has to identify, you're giving 3 words, but I think the translation is 4 words. And then after the translation is done, it actually has to tell the human being, I'm done. And that is by outputting EOS. So a single LSTM can do this activity, and this is called sequence-to-sequence model, where you input the sequence in a sequence, and the output also comes out in a sequence. That's called sequence-to-sequence model. Mathematically, I know sometimes I think it's difficult for people to understand the mathematics, and for me too. I think when I started studying this thing, I think, oh my God, it's a long time ago I done with the university. Now I'm going back to the university. The probability of the output y1, y2, y3 till yt dependent on x1, x2, x3 till xt. The t's are too different, just to signify that the number of outputs not necessarily be exactly the same number of inputs. That's only, but otherwise just use the c. So to say t prime and t. So mathematically, what I'm trying to show in this is the probability of for these to be the outputs based on these inputs is very similar to or same as the product of all probabilities of each word. So yt in this case can be from t is equal to 1 to t prime, that is y1, y2. So each output y1 is dependent on all of the previous outputs and v. V is the last hidden state of the LSTM. So after the end of state, there's a hidden state of this LSTM. So all of the W, X, Y, Z, they are dependent on the hidden state of LSTM at this time and the previous word. So if let's say if you take this instance, X, the probability of X is dependent on the hidden state of the LSTM and the previous word that was outputted. That's how you have to read this mathematically. So now tell me, will it put you to sleep enough or not? Let's say in the nights, I think if you really want to sleep, you start reading this, I think you'll fall asleep fast. So I'll pause for a second and then tell them, because I think there's going to be such similar mathematical equations coming up. And I wish I can teach you guys NLP without mathematical equations, then I'll be preaching something which you just have to believe me. But if you want to show me the proof, then I only can show proof using mathematical equations. V is the hidden state of the LSTM. So it's H or V. Again, different people. So in this paper, I picked up everything from this paper. Here they are using hidden state as V. Typically, nowadays many papers use hidden state as H. Yes, sir.
Yeah, so the input to this could be words or POS tags. If you use POS tags, you could.
These are all words, but when I say words, these are all vectors, the word vectors. So it will not understand the word. You have to actually convert the word into a vector. But for our discussion, when I explain a concept, I'm trying to say, okay, we are inputting a word, but in reality, you're actually inputting a vector, and you're also getting vectors out as an outputs too. From the vectors, you got to have a mapping to the words, and then you can that the LSTM can figure out.
Right. And you can extract, like you can learn from that, like say, you can apply POS tag, subject verb object is a, a very common, noun verb nouns, and other things aren't.
I didn't get your question. Okay.
You could extract knowledge then from a model by retro POS tagging all the words.
There's no more POS tagging, etc. What's happening here? So let's say you give a sentence, the cat sat on the mat, and you want to translate that into a French thing. And now let's say, let's give a human being so that I can pick up the gender. John wanted his car to be serviced today. So the word his refers to John because it's a male as a gender. When you translate that into in let's say a different language, I don't know German and French, but I'm just saying in German and French, the John word I think will come as John, but then the word his, if it's an exact translation, it's fine, but I think the model has to figure out the translation for his into French, which may have an impact on the gender of the subject, and hence I got to pick word A instead of B or C or whatever. So that knowledge is hidden in their hidden state, and that's captured. Now, by the way, when I say ABC and then it starts translating, you've got to actually train the model with lots and lots of text. I'm just giving an example of a simple ABC, but just an ABC, it won't translate unless you have a trained model already available.
Those commonly be like word to fact continuous for representations.
Yeah.
For the ABC.
Yeah. I'll talk about word to vec because that's a slightly complicated concept. I thought I'll talk about these models first and then I'll come to it.
Would there be a scenario where the events are independent?
In what way?
The conditioning the model y1, y2, y3, so
No, it cannot be dependent. No, it cannot be.
independent.
It cannot be dependent in the sense y2, y3 may be influenced by y1. Again, as I mentioned to you, sometimes the gender of the subject or the past, present, or the temporal aspect of it also may influence what the words are going to be. So let's say y3. For the model to predict what is the right word here, let's say at this timestamp, it's giving an output of y. What it's actually doing is, it looks at all the vocabulary available. Let's say if you have 50,000 words, it gives a confidence level or a probability number for each of the word in the vocabulary at every time step. So the reason it picks up y is because y has the highest confidence level based on the previous outputs, w and x, and I'll talk about why the same model things are going in a minute, but it picks up y because of two reasons. One is, of course, the confidence level of y at that time, based on the time hidden state, and also what were the previous outputs of the model. So these, and there's so many other factors too, at least these two, but I think so many other factors which actually influence. So from that sense, y1, y2, y3, y4, these are all kind of dependent on each other. And they are in turn dependent on x1, x2, x3, x4 too. That's why I think the probability of these outputs dependent or based on x1, x2, xt is very similar to the probability of each word to the previous inputs and the hidden state.
So after US, let's say the his came after the end of this sequence. How does the let's say the his was not in the first sentence, but it's in the following. Like it starts after the period, then it starts off with his, whatever his.
Yeah, good point. So, so you give only one.
Wanted to service it today.
Yeah.
But the John was some different sentence.
Yeah. So, and that's a good example. You should actually even do Google API actually has a translation. If you go give it a sentence there. If you give only one sentence and ask for a translation versus actually it's two sentences, but you only did not give the second sentence, but there's some message in the second sentence which is influencing the first sentence, it makes an error. It makes a prediction, but sometimes it could be a wrong too, because I think you're not giving the complete. That's why when you do a translation, even if you do a Google app, the voice translation, you have to talk the entire sentence, whatever you want to talk. Let's say you go to Brazil, you go to France, and they say, what is the name of the restaurant which is on this street? You have to give a complete sentence, and then only the model translates, because it wants the complete input. If you give half the input, it translates is going to be erroneous. So if this, like in your question, if the word, what if the word comes, then it's going to be a wrong translation or wrong output. Whether in this case, I'm taking an example of a translation, but it could be a summarization activity also as part of NLP. That's going to be wrong. So the model will continuously read till your end of sentence. And the end of sentence in this case, when I say end of sentence, I'm saying end of your message. If you're done with the message, then I think it starts translating. Yeah. So this was the first model people suggested, but later on they came out with a different thing. Okay, instead of using the same LSTM, can we use two different LSTMs? So they said, okay, fine, we'll have two different LSTMs. One is called encoder LSTM, and we have a decoder LSTM. All that is, this is concept is different from the previous one. Is all the inputs are fed into one LSTM, and at the end of that input, the LSTM will have a hidden state. Take just that hidden state and pass it on to a decoder, and then it starts using the decoder to hidden state of the encoder to decode. I forgot to explain one more thing. Now, the first output is W here, and then the next output is X. If the model, initial researchers found that if you reintroduce that initial output back into the LSTM, the probability of accurately predicting X goes up, because the model now knows what my previous hidden state was and what my previous word is. And based on these two information, it makes a better accurate prediction. Earlier, when they did the experiments, when they did not do an input again in, it does not know what the previous output was. It just only considers the hidden state, and then it was not as accurate. So you re-input the previous output into the model to improve the accuracy. That's what is happening there. What I explained. So now I'm not showing that concept here because we already know the concept to reintroduce the information. But here I'm trying to highlight the encoder and decoder concept, where instead of having one single LSTM, you actually can have two different LSTMs, and then the encoder LSTM's last hidden state is passed on. And when I say last hidden state, like that is actually H3, because at every timestamp the hidden state gets updated, and then in this case we are only considering the last hidden state, because the research says that it is encapsulating information about so many different inputs into the last LSTM, because it's constantly updating, and hence the last LSTM will have information about all the inputs.
So now there are weights representing weight.
Sorry?
I mean, now they're representing weight or something else.
I didn't understand your question.
I mean, the topic,
Those are the weights, yes. Because it's the same LSTM, so there's the same weights are being shared.
What's the dimensionality of
The here dimensionality, you have to prescribe when you run a model. Sometimes people have used a dimensionality of 512 dimensions too, but I have run a model for my question answering as low as I went to, I think, 4 dimensions, and then I went to as high as 512. But I think anyway between 16 and 32, the model I think was doing a decent job. Compared to 32 dimensions versus 512 dimensions, the model did not significantly improve in accuracy rates. So I did not see, except the fact that it took a lot more time. Because if you have 512 dimensions, then there's so many computations happening, and then if you have multiple layers, then it's going to take even more time too. So you can prescribe. I think when you define a model, you have to mention what should be your dimension size, the size of your network. Yeah. 8 and 16. 8 and 16. Sorry? I have used a data On the tweet analysis, I think I had 1.4 million tweets. Still, I think I was using 32, I think, dimensions size of LSTM. For experiment's sake, this one particular, the last experiment, I actually did all 4, 16, 32, 64, and 512, I think I did. 512 took considerably more time, but 32, 16, 32 I think is fine. 8 is fine too sometimes. Size of the dimensions of your LSTM. Okay, so this is the encoder-decoder approach, and the encoder-decoder approach is actually mathematically can be represented this way. So the encoder, you have a hidden state, is some sort of a function based on all the inputs. So a hidden state at timestamp t is dependent on the input at timestamp t and the hidden state of timestamp t minus 1. And the output vector, which is sort of an output of if you want the output of the LSTM, is a function of all the hidden states of the encoder. And those functions f and q are some sort of a nonlinearities. There are so many nonlinear equations available in LSTM in NLP. And the decoder works on the probability of yt at any timestamp t dependent on the previous outputs and the context vector. The output vector is also same as some sort of a function of the previous output, the hidden state of the decoder, and the output vector of the encoder. So this is an extra complication I'm introducing now. Let me show the picture. So when you give all the inputs, it has a hidden state updated constantly. So you take this hidden state and pass it on. And the y1 as an output is based on the hidden state, but it is also dependent on its own hidden state. And when you go to the next timestamp, y2 is dependent on the new hidden state of the decoder and also the hidden state of the encoder. Encoder actually is capturing all the inputs, so you need that. But also the hidden state of the decoder is required at every timestamp because it has to remember or know what is that I have outputted till now. So let me show the equation again. So decoder, the probability of yt based on all the previous outputs and the context vector of encoder is same as a function of previous output, the context vector of the decoder, and context vector of encoder, which is actually hidden state of encoder.
If you go back to that, so what's the difference between this S and the H? They're all hidden state.
Yeah, these are hidden state. The S and H I'm showing, S is the hidden state of the decoder, and the H is the hidden state of the encoder. Okay, so some researchers, there's one paper published here which said instead of just having an encoder and decoder where when you are decoding, instead of depending on the encoder's hidden state, can I look at the encoder hidden state at every timestamp? So what I was doing here was, in the previous model, show this picture. The hidden state of the encoder H3 was passed on, and then that H3 was used to compute the hidden state of the decoder, and that was being used to make multiple outputs. A new research proved that if you have a peak at, instead of, this is the encoder and that's a decoder, this is the encoder hidden state, instead of just only giving it one time, can I give that to the decoder at every timestamp? It's called peaking. Having a peak at the encoder hidden state at every timestamp also helps. So this is relatively simple relatively important, but the most important concept in NLP is attention. This is used in multiple locations for translations and summary and stuff. Let me take an example in the context of summarization. Let's say you, or even translation too, let's take an example of translation. So you have an English sentence and then you actually have to translate into a French language. Let's say the input was 10 words long in English, and then the output is, let's say, 7 words long in French. And the 6th word, when you're making a translation, creating the French word, 6th word in the translation, the model has to understand which word in the input should I be paying attention to. Because just because it's the 6th word in the translation does not mean that you should only look at the 6th word at the input. It could be the 2nd word, or 1st and 2nd word, or maybe 2nd and 5th word. We don't know. For the model to become intelligent enough, it's like a human being. Like when you are translating, you want to, after 3 or 4 words, you want to go back and read the sentence again. And this time you will, even though you read the entire sentence, but you pay more attention to a few words. So attention, which is same as when you're doing a translation or any other NLP activity, the model will go back and look at the hidden states of encoder, but it wants to pick only the hidden states of some inputs, or maybe x1 and x3, or x2 and x3, whatever. It identifies, based on the training it gets, it knows what words to pay attention to. So attention as a concept will allow the decoder to go back and pay attention to those specific and relevant words of the input. Whereas in this model, it is getting the entire hidden state of the encoder. So it has access to all the information in one go, and the model does not know, okay, which word should I pay more attention to when I'm making my 2nd word translation? Should I pay attention to this or this or this? Whereas in this approach, it's just giving H3, which has all the information together. It says, no, I don't want all the information. Tell me more about 2nd word. That's what attention is. And mathematically, well, that's the conceptual explanation of attention. But in this actually is a complicated picture. Let me go to the next picture and come back to this again. Yeah. So you have the encoder, or the input information coming in. Attention, you devise a mathematical equation which takes into consideration all the hidden states, and based on and you train the model in such a way that at any timestamp t, it looks at the hidden states and picks which hidden state should be looked at more carefully. So there is a factor called alpha, a multiplication factor or an average factor. The average factor will give a number for h1 as 0. That means don't look at this word, and also may give a alpha as a score for hn as 0. That means don't look at h1, but it may give a factor of 0.7 for the word h2. So say look at the 2nd input and hence the 2nd hidden state, because the average alpha factor for that number is high. And if it's a fraction of 0.5 and 0.3 or 0.2, that means it's actually asking you to look at 3 different words, input words, and not one word. So going back to this mathematical equation, so it's doing alpha here, it's multiplying the hidden states of all the inputs, and when you're making yt as a prediction, it looks at what the score for alpha can be, and based on what alpha number is for h1, if it's 0, then it doesn't look in here. If the alpha factor is, let's say, 0.7, it gives 70% weightage here, and the rest of the 30% weightage here maybe, and the rest of the alpha numbers will be 0, so don't pay attention to any of those things. That's called attention. Yes, sir.
Is that a 2-layer or 3-layer overlay?
Right here, this is actually a 2-layer where you have a bidirectional LSTM. Actually, I didn't want to explain the concept because I think we didn't talk about it. But instead of having one LSTM, here what the researchers have done in this paper they actually have two LSTMs. So one LSTM, they are giving inputs in the correct sequence, and the second LSTM, they're giving inputs in the reverse sequence. So let's say the cat sat on the mat, then another LSTM is getting mat the on sat cat. The logic in that is, when you're giving the first word the, sometimes and the next word is the cat, so by the time you look into the word cat, it knows what the previous word was. Sometimes it wants to know what the next word is too. And to know the next word is, sometimes if you give the sequence in a reverse order, you actually can know what the previous word was, or the next word is going to be. So bidirectional LSTM as a concept is used where at any timestamp, you not only know the past, you will now know the future too, because you have given the inputs in a reverse sequence.
Sure. But yeah, I mean, it's kind of like a four-man parse tree. We don't really know the parse tree. But why is it better to use a tangent activation function instead of linear?
Why is it better than?
Yeah, the activation function in your RNN is tangent. It's not linear. If you're trying to learn that multiple words in that sentence might correspond to.
Where's the tangent?
On the next line.
Okay.
You have the tangent.
Tangent you're talking about?
Yes.
Yeah.
Why is
So,
it use tangent instead of?
there are multiple nonlinears. Tangent is one of the nonlinears used. I think ReLU is another nonlinear being used. In this case, the researchers have used tangent in this case, and I don't know the exact explanation why this makes sense. But by default, I have seen any of the nonlinears used. Most frequently used ones are ReLU and tangent.
I'm trying to say why is intuitively why does it feel more right to use nonlinear later? You're trying to learn that multiple words in the input.
Okay. When you do a nonlinear, the entire concept of nonlinear is when the model is outputting numbers, you want to squash it down to the number between a range. Let's say 0 and 1, or -1 to 1.
So kind of like regularization.
Yes. Yeah, it's a regularization. Yeah. Correct.
Just to check my understanding, so the attention layer, one of the things that implementation helps with is if you're doing a translation and the word order changes, then for what you're outputting, if the third word there actually depends on the fourth and fifth words of the input.
Yeah.
And that's what the attention helps with.
Exactly. That's, or even summarization. Let's say if you have 10 sentences has to be made into one single sentence, then which of these 10 sentence words need to be paid attention to also helps in the attention process.
Okay.
And it also goes back to your question answering. Let's say if you have a question and the model narrows it down to a passage, it has to know out of these 100 words, which words I need to pay attention to find the answer for my question. So any of the NLP model, when you have a bunch of text that's coming in, instead of having the entire text, I think when I started explaining LSTMs or RNN, I said, okay, if you have 100 words, give all the 100 words and it becomes intelligent enough of all the 100 words, which is fine, but if you want to fine-tune the activity of the LSTM, while it's outputting some things, it may want to go back and check, what's the 45th word? So that attention will help going back. So having the hidden state of the entire input text also helps. Plus on top, if you have an attention layer, it goes and looks at specific words, a specific collection of words to fine-tune the output, whether it's translation, question answering, summarization, whatever it is. So it helps. So attention, the hidden state plus attention layer together will enhance the accuracy.
Thinking like an example would be in English, like got out of the car, in German, and Paris after Wagen ausgestiegen, because there's a compound word at the end of the sentence, and it corresponds to got out.
Yeah, I don't know the German, but yes, that's the conceptually yes. It goes back and looks at the gender, the temporal aspect, compound words, all of those things. It goes back. Yeah.
Question. So the alpha is the weight for the attention, right?
Mm-hmm.
And so the all alpha has to sum up to 1.
1, yes, absolutely, yeah. Attention again, another layer. I think it goes back to a different paper again, where they proposed different types of attention, where they want to enhance the accuracy because of attention. In this case, you have the inputs, there's something called skip level inputs. So when you have multiple layers of LSTMs doing an encoding activity, normally the stacking of LSTMs, you have the input going into the first level LSTM, and the output of that LSTM goes to the second level, and the output of that goes to the third level LSTM. That's how you actually normally stack LSTMs. The reason why you stack LSTMs is it actually captures information better even. It's actually a lot more precise. So people actually do stacking. But the problem is there's a limitation on the stacking too. The more stacking it is, it's computationally expensive. You've got to have massive GPUs and CPUs and more memory, more time, all of that stuff. So there's a limit of that. So without stacking too much, you can still have it stacked, but to increase the accuracy, you can also have a skip level inputs where the output is not only goes to the immediate layer above, but it also goes to the one layer above. So the second layer gets not only the inputs from the previous layer, it gets the inputs from the one layer before that also, so that the information that may get missed out from first to the second layer will not happen now, because I think that this layer actually has access to the information from the previous layer. So that's the skip level, which is more of a fine tuning of your attention. So attention is have a average alpha numbers for attention, and then that is helps you to pay attention to which words, but you can also increase the overall accuracy by having skip level. In this paper, people have proved, they have proved a few things. I did not introduce the term GRU, gated recurrent units, or another variations of RNNs. So first were RNNs, and then came LSTMs and GRUs. LSTMs have 4 layers. I think I explained to you 4 different layers, and 3 gates and another layer, 4 layers. GRE has only, I think, 2 layers. People felt GRE is going to be computationally simpler, but the eventual results prove that LSTMs are far better than GRE. So if you are trying to define an NLP model, and some experiments in NLP, and if you want to use, if you are confused between LSTM and GRU, by default start using LSTM. Also, even though logic explains that the deeper the network is, if you have multiple stacks of LSTMs, may sound better, but sometimes for the, especially the encoder part, it's better to have a shallow networks, not 2 deep networks. This is, yeah, explanation of now, so let me, I'm trying to see how much I can cover. I explained this conceptually, and it sounds so complicated. But when it comes to implementation, remember I explained about just a sequence-to-sequence model? It's just a one line. Model is equal to simple sequence-to-sequence, and then you identify the various dimensions and inputs, and that's it, you're done. You are defined a sequence-to-sequence model, and I showed you a picture with a peak, where you want to constantly go back and check the hidden state of the encoder at every time. All that, it's exactly the same, you just have to say peak is equal to true. So if you pick Keras as your framework, of course there are similar models too, even TensorFlow and Piano, and I don't have working experience in Kafka and other places, but they also may be equally good. But the programming aspect of these solutions are extremely simple. Like peak, all that you have to do is just peak is equal to true. And if you want to implement an attention, which seems to be so complicated, identifying the alpha numbers and what fraction to take and all of this stuff, it can be just that you pick the attention model, attention sequence, and that's it, you're done. So when you want to do an NLP, I know the organizers at this conference, I think, wanted me to talk about hands-on other stuff. The hands-on part is the simpler thing. The implementation is easier. Of course, it's not trivial. You got to do a little bit of study there too. But conceptually understanding is a lot more important. If you don't understand how attention works, if you don't understand how sequence work, how a hidden state works, doesn't matter whether the library is available, because sometimes you just don't know which one to call and what function to call. Now let's talk about word to vec. This is an extremely important concept. We talked about one-hot vectors, and we talked about co-occurrence vectors. I think in the last 1 year, 1.5 years, Google came out with a new method called word-to-vec, and there's another, no, Google came out with a method called GLOVE, Global Vectors, Glove. Word-to-vec, I forgot who actually invented it. Word-to-vec is another approach, and I have used word-to-vec. I've not used GLOVE as extensively, just once I think I used, but I've used extensively word-to-vec, and I've used one-hot vectors. I've found one-hot vectors sometimes very, very effective, and I've found in some other problem statements word-to-vec also very effective. So if you are trying to use NLP models, and if you wanted to use what type of vectors you want to create, you can go for one-hot vectors. Again, creating one-hot vectors is very simple. It's just a one-line program. You can just call and then it creates the vectors out of the vocab. And word-to-vec is also one line, just a simple one line based on the vocab you're giving. It just gives you a vector line. But conceptually, the word-to-vec is created, that is creating vectors out of words, is done in two different ways. One is continuous bag of words, and the second approach is skipgram. In continuous bag of words, the approach taken to create a vector is you are predicting what the next word is based on the context, that is based on the previous and the following words. And it can be one previous and one following, or two previous, two following. So it can be whatever it is, and that's called a window. If the window size is 4 or 5, then you have 2 and 2 of each side. So depending upon how large the window you want to pick. Of course, if you're creating a word-to-vec using a large window, computational becomes expensive. But people have found a word, the meaning of a word is influenced by not more than 7 words on either way. In normal English language, people have found a word is the meaning of a word is influenced by not more than 7 words before or after. You can say, okay, maybe the possibility of a word getting influenced by a word which is 1,000 words ahead or follow is quite rare. That's what. So the windows, you can pick a window of 2 or 3 or 4, depending on what you want. But typically, I think people take 2 as a window where they actually have 2 words before and 2 words later. And using the context to predict the next word is the approach for continuous bag of words. In skipgram, using the current word, you predict what the next words are. The previous words are the following words. Those are the expressions. But I don't want to get into too much of explanation because the implementation of this word-to-vec is very, very simple. Just had a one-line code and calls. Right.
Brief question. What do you do at the sentence boundaries? You know, for the word 1 or 2
Yeah.
at the beginning or end.
So
Is there some like null or?
So typically, I think they put the end of sentence notations at the end. So if you have a 2 window, you take period also as a word, and so if the window is longer than that, you actually start putting unks, and hence UNK unks. But then having a larger window also does not make sense towards the end of the end of the sentence words. But on a large vocab, that averages out. So even if you have a window of 2 and you have a last word, what would be the next 2 words? You'll actually put a period and a unk next to it, and then still try to make sense out of it, and the effectiveness of word-to-vec is still high. Okay, so let's run the word-to-vec.
Is this applying a pre-trained Google word-to-vec, or is this training a word-to-vec?
This is actually training the actual word-to-vec, the code, which where is that? So this is available in TensorFlow. Let me see if I can show you the whole thing. This is from TensorFlow, the actual implementation. So when you use the word-to-vec in your actual existing program, this gets called. So you have the TensorFlow in the background running, and the whole file gets executed. I just want to show what the file is and how it works. But when you use a word to vec, when you're creating a vector out of a word, all that you have to do is just give the word and then say word to vec, and it actually converts that into vector and gives you a vector. But in the background, what it's doing is actually it's picking up. So it actually has, it's based on the data set. So it actually downloads, I don't know, this file, whatever they're picking up. So we'll download the file if it's not downloaded already, read the file, identifies what the size of the vocabulary is, then build a data set out of it, and then it make batches out of the vocab and then runs the batches.
Is there stop word removal or stemming or?
Let's see. It has unc words. I think it puts in uncs. Because typically I think they call multiple files from each file. So I don't know if one of these functions actually is calling lemming and stemming. Yeah, I don't know the answer for that question. But if I go look into the code, I think I'll figure out. But I think from this file, I'm looking at if it's making any API call for lemming and stemming, but I'm not seeing it. So skip window, it talks about how many words to consider left and right, and number of skips is the number of times to reuse an input to generate a label. Embedding size is the size of the LSTM, the dimensions of the LSTM, and then batch at how many inputs per run. The best part is it actually creates, I think it creates tsnif file too, image too. Let me see, that's what it actually is doing.
Just
Yeah, it does it.
Data set with most common words.
Yeah. So I'm actually running it now. It takes, so it's down. I already run it once, so it's not downloading the file anymore. It's actually, otherwise it downloads the file. Text8.zip. I think that's the file. I think it's referring to the data set. So data set data size around 1.17 million words. The most common words are uncs. There are around 500,000 uncs and almost 1.1 million these. I think it's taking off those words. I think stoppers. I think it's taking off. But again, so it's what it's computing. It's actually computing the nearest words for some random things, like nearest to the word it's. These are the words it finds, and it does that. It's doing multiple epochs. So if you look into the code here, I think it's supposed to run 100,000 times, I think. So you have 25,000 steps done. If you have on your machine, if you're running it, the best part is, I think I already have it here in the file. It actually creates a file called tsnif.png. This is actually a file on the same data set which I've ran yesterday, so I'm just showing it to you. Even though the file is running right now, it will take, it's not more than a minute, I think. It's already 44,000. 100,000, I think, will be done another minute. So I think tsnif is here, yeah. So this is the two-dimensional image of the words converted into a vector. So when you create a word into a vector, it's a number in a space, not 2 dimensions, it could be hundreds of dimensions. Now humanly it's not possible to visualize such a word embedding. So let's say you actually have words in the space hanging, and it's hundreds of dimensions. To understand that, you actually have a tsnif image which tries to consolidate into a 2-dimension image. And these are the, I don't know that I can show. Look at, so based on the data set given, the word and, because, use, they appear closer to each other. So they are almost kind of similar. They appear close enough to each other, and so this is the similarity and cosine similarity, etc. These are some of the mathematical terms being used. These, so in other words, is the word law and the word, let's say, water, don't appear close enough. They don't appear commonly together. They're not in the same sentence. And that information gets converted into vector also when you're making a vector out of the word. So this is the two-dimensional image of the words converted into vector, which will show which vectors are closer, which vectors are too far away, which also shows which words seem to be occurring closer, seem to be occurring so far apart. So, yeah, let me.
What is the color?
Color, yeah, it's a good point. Actually, I need to read the file, but I think it's various classes. I don't know the answer, sorry. Yeah. But typically the TSNE image I think is shown, is trying to boil down a multi-dimensional image into two-dimensional just to visualize. If you run the same file one more time and then do another two-dimensional, it may pick some other dimensions and hence the image may look different, but the words that appear closer to each other than the words that don't appear to close enough to each other will be relatively same in any image you're going to create out of it. So let's go back to my file. I think it's done. Yeah, it's done now. So if I go back and look at, see, it's created just now. It's 12:01. Yeah. So I can open this. Let me first close this. So it's so the word important and open seem to be occurring close enough frequently for the model to figure out the vectors in such a way that when you represent the vectors in a two-dimensional image, you can see the words also occurring together. That's the beauty of word to vector. Similarly, I think GLOVE also, global vectors method approach by Google also it has a great capability. So using word to vec to convert word to vectors actually is more effective because it actually captures lot more information of a word, co-occurrences, the sentences, where it occurs, how frequently it occurs. There's so much information it captures into a vector, and that's a lot more useful when you're using those vectors to compute your NLP problems. Okay, let's get back to our presentation. I wanted to show you a Keras model, but which is not necessarily NLP problem, but I just wanted to show you how simple it is to define a model using Keras framework. If you don't have familiarity with any framework and if you want to start using, I would prefer to use a TensorFlow because it's actually a lot more flexibility and a lot more deeper. They can do a lot more things, but Keras actually works on top of TensorFlow, so you can use TensorFlow as a backend for Keras, and then it's very, very simple to write a model. In 3-4 lines you can write, and I wanted to show this example where this is not an NLP example, this is a machine learning example of trying to predict the Pima Indian women, the probability of they getting diabetes in the next 5 years based on this data. Just based on these 8 different items. The number of times pregnant, plasma glucose concentration, this diastolic blood pressure, the skin fold thickness, 2-hour serum, BMI, diabetes, and age. Just those 8 factors, I think they have a data for I don't know how many patients they actually had. And a class variable, there is prediction, yes or no, whether they got diabetes or not. And it runs beautifully, and the model, I think it just takes, overall, the entire neural network to define this problem statement is, I think, 10 lines. You will be amazed. "23 lines. Entire model is only 23 lines to run a deep model using Keras to identify, to classify this data, PIMA patients, to identify who will get diabetes in the next 5 years and who will not get diabetes. 23 lines. That's what I mentioned earlier too. To define an NLP model in using deep networks is very, very easy based on the frameworks given. But conceptually, I think people need to understand. I think you've got to understand how attention works, how sequence to sequence works, how the dimensionality of your model works, what is fully connected versus sparsely connected models. You've got to understand that. For example, here is dense. You're actually, model add is you're just creating a first layer. Another model add is creating a second layer of your neural network and a third layer of your neural network. And for each network, you're defining whether it's a fully connected network or not. So dense called densely connected is fully connected network. And what will be the dimensionality of that? How many neurons in that layer? And the input dimensions and activation. That's it. This is just the one line creates one layer of your network, and you have 3 layers you're creating, and you're defining the model, then you're asking it to compile, and the compilation is how to compute the loss and how to optimize the loss, that is reduce the loss. So you have a loss parameter and you have an optimizer parameter here. Then after that, all that you're doing is, okay, now run it by giving the data. So I've designed what the model is. I told how the model should compute the loss, and then when the model is defined completely, you fit the model, that is, you run the model with the data given. X and Y is the data, and you defined what the data X and Y is here. And that's it. After that, you do an evaluation which actually computes your accuracy rates. The whole model will run, I think, in less than 2 or 3 minutes. I can run it for you guys.
That's an in-sample evaluation.
Sorry?
In-sample evaluation as opposed to on test data.
This is, yeah. It's an evaluation based on the test data. The accuracy prediction is based on the test data. So it actually takes, I think, 10% or 20%, I think, data aside for the testing purposes, and it computes the accuracy based on that for the 20% of the data. Yeah.
Was this done with other in-sample evaluations to compare?
The framework, this is Keras framework, and you can also use TensorFlow. There are a lot of other frameworks available too. Yeah.
Oh,
Yeah.
What it used underneath, I mean, it's just deep neural network.
This is a neural network. The way of defining is neural network. I think this is running on top of TensorFlow. So when you say model add dense 12 input dimensions equal to 8, it knows what API calls to make into TensorFlow to create a model. And then so when you're designing the model in these 3 lines, then you're telling the model how to compile or how to compute the cost and the loss and the optimization. And after that, you're just giving a command, okay, run. It uses the TensorFlow framework and picks up the right API calls and passes the data to those APIs, and then runs the data for you and gives the eventual accuracy rates. And here the accuracy you're trying to predict is, the metrics you're predicting is accuracy. Where does it say accuracy? So let me run it for you. It will show.
So how is it connected to NN? So I think I just got lost in the connections.
This example, I think I mentioned to you all. This is not an NLP example. No,
Okay, you're
it's
just
not.
showing it for just
I'm only
the
showing this to show how simple it is to design a deep neural network using Keras. Because see, so what I'm trying to do in the whole today's session is I'm introducing various topics of NLP, but I'm also showing some implementation details about how easy it is to do the POS tagging, the NER, and all of the other tagging. But if you want to really run a deep neural network on this, I can't run the entire deep neural network in the class today because it's going to take multiple hours to do. But I just want to show an example of if you want to do Keras, in 23 lines you can define a model for this data set. You can do maybe 50 lines maximum or 100 lines maximum for any other NLP solution you can work on using Keras. But of course the flexibility is lost because it's a little more an abstract level code. But if you really want to do further customization to improve the accuracy, final 2 points extra, and also make it faster, you can go to TensorFlow and other stuff. But I just want to show this example as.
Keras is that framework, but makes calls to TensorFlow
Yeah.
API.
So Keras uses TensorFlow as backend, yes.
Yeah, but you're running it on your.
TensorFlow and Keras both are running on my machine, yes, on this laptop. Yeah. So if I want to talk about translation, how to do the translation, so you have to start with the sequence, and then of course you use the encoder-decoder, and then you add on top attention model on that. Then you also do a language model. So let me see. So this is a language model. What is the meaning of a language model? A language model helps you in so many different ways, but let me explain. Language model is a deep neural network where you are training the model to understand how sentences are constructed. And eventually, when you give an incomplete sentence, a language model will predict what would be the next word and the word after one and the word after. So it is like a human being which has read, let's say if it's based on Wikipedia, if it's read all the Wikipedia articles, and now if you give it a new sentence, it can predict what the next word is and the next word is. And this is actually used for so many NLP solutions. And there are two types of, if you look into language model, when you're training, you give an input A and it makes a prediction of B, and then reintroduce a B to it, and then it makes prediction C, and then it becomes a little more smarter because now you've given C, and when you input C, it gives an output D. This process goes on until the millions and millions of words you want to train. So this is during training. When you're predicting, you give the first word and say, okay, now create a story for me, a new article for me. It makes a prediction B, and then it just gives that B back into it so that it actually predicts a C, and then it goes back into it. So that's what during generation. Language models are used to do so many different things, including language creation. So you actually can create stories. The Shakespearean example I gave you earlier was done using a language model. Yeah.
Would you mind if I announce our terrorist training class?
Sure.
So I'm one of the organizers for a local meetup, ACM, Association of Computing Machinery. And we have a 2-hour Keras class on Saturday, October 14th. It's part of the data science camp, day-long event that is for up to 420 data scientists. So I'll leave some business cards out if you want to look at it later. What's that?
Oh, what's the format for PD?
What
What's
is?
the cost?
Oh, like $60 for the day.
Yeah, thanks. In machine translation, in this paper, the author said to increase the accuracy of machine translation, where you give an input and then it gives an output, you can increase the accuracy by adding a language model to it. So in a regular neural machine translation or NMT model, based on the encoder's context vector, the decoder will have its own hidden state, and based on the hidden state, it actually starts making predictions on what should be the next word in the translation. But instead of making one word as a prediction, the model can predict what are the top 5 words that should come here. And if you are not sure which is the right word, you can club that with a language model, where the language model looks at what was the words you have predicted till now, and what are the new word, the 5 choices you are giving me. So let's say you have an incomplete sentence and 5 choices what the next word is. So I have 5 sentences, and language model will look at all those 5 sentences and say and tells you which sentence sounds more accurate, more precise, more makes sense, and hence the accuracy of the overall translation goes up using a language model. So actually it's 12:15 now. I know we had to end at 12:30. So I can pause now, and if you guys have any questions, we can talk. There's a lot more stuff I wanted to cover in terms of. Let me see if there's anything.
Would you consider covering the episodic memory?
Episodic memory? No, actually I took the slide off.
Okay.
The presentation you have, I think I modified that. That one particular slide I changed. This, maybe you want to read this paper. It's called the Google's Neural Machine Translation System. It's a massive model they trained, just released I think in 2017, Jan, Feb, March sometime. I'm not sure. they have used so many additions in this machine translation. I think the API call, which is available on a public forum and in Google, if you go to Google machine learning, I think they use this model in the background so that if you, when you give a sentence in a language and then wants to translate to a different language, I think it's using this model. So it actually has 8 layers of LSTMs, both on the encoder side and the decoder side. They actually have, and the first layer has a bidirectional LSTM. I think I mentioned to you earlier, if you have bidirectional, you have the input sent in one layer in a regular sequence, and there's a second layer in the opposite sequence, so that the words, I think, are closer to each other. They have used residual connections. I explained that concept too, where for every layer, instead of just it depending on the previous layer's inputs, it in the residual connections, it also depends on one layer bottom to get the connection, so that the middle layer should not miss out on any information. So that's another residual layer. They have used attention method. They have used low precision arithmetic during inference, where they found if it's a 16-bit or a 32-bit or 64-bit predictions, it takes a lot of mathematical computations, but the accuracy doesn't drop too much if you do lower arithmetic precision, and that's another. Beam search is another concept I did not get a chance to introduce. I wanted to really talk about it. Beam search is the following. Let's say in a translation or even summarization, you have the incomplete sentence and then you have the next word the model is trying to predict. Now, instead of predicting only one word, the top word, which the model thinks is the right word, you can actually ask the model to predict the top 5 words, top n words. And then you have the top n words, let's say n is equal to 3, then you have top 3 words. When you make the next prediction, for each of the 3 words, the next word, it gives a confidence level for the entire vocabulary. So if you have a 10,000 word vocab, for the first word and what would be the next word after that, it picks a confidence level for all the words. So the word after the 3 words, the first word, and word 1 in the vocab, word 2 in the vocab, word 3 in the vocab, word 4 in the vocab, it puts all the words and computes a confidence of this combination. And it repeats for the second word and repeats for the third word. So if the vocab size is 10,000, you actually have 30,000 choices for what would be the combination of the next 2 words for this incomplete sentence. And if you go on, if you keep on doing it, then the numbers are going to be massively high, because 30,000 times 10,000, the next word is going to be. So beam search, what they do is, if you identify the top K is 3 or top 5, or it actually identifies the 3 words, and the next word it will identify of all the 10,000 words, it takes a combination and only takes the top 3 of the combination which has actually highest value, and then it moves on to the next word. So that's a beam search, which actually normalizes the length and also does the coverage penalty. In a sense, coverage penalty is how many words are being covered in the vocab, so that there's an accurate translation happening. They also have a solution for rare words. Let's say if you don't have a word in my training vocab, but in my inference, you're asking me to translate a word which I never saw, then they have a solution, a newer solution. Typically the solution is, standard solution is, if the model has not seen a word ever and you're asking the model to translate a word now, it actually puts an unk word there, but they actually have found a newer method. It's a good paper, I think, if you guys are interested in reading. And it's 12:20 now. I'll pause, and if you have any questions, I have a few other slides I want to talk about. But I guess the 9 months of study, I cannot do it in 3.5 hours, looks like. But if you have any questions, I'll be happy.
How do you get the slides?
Okay, it's here, my GitHub link. Okay, that's my GitHub link, and all the Python files I've used, instructions, plus the presentations, all of there.
If I missed it, did you give any recommendations on toolkit?
No, I did not. For playing, I suggested just play with NLTK as a corpora available, and there's a lot of even they have their own libraries too to play with the text and stuff to understand NLP stuff. But if you want to use a framework to build your models, I think I would say as a beginner you can start using Keras, but really people are using TensorFlow if you want to really do a deeper, more capable files. I think it's a good idea to use TensorFlow.
But as to NLTK?
Yeah, NLTK.
Yeah, the general word in the market, NLTK is essentially mothballed 4 years ago. It hasn't exactly developed at all.
That's true. Yeah.
They could just busy. It was passed out by Spacey Daniel at least 2 years ago.
Yeah, yeah. Even I think Stanford and NLP also has different corpora, different libraries. Yeah. But this is the for someone to play, if you're a beginner and if you want to play around with some stuff, if you want to have access to lots of corpora and then some frameworks, some libraries to play with it, I think this would actually suffice.
Exploit patches Encoder corpora, and the porters down sucks, and a bunch of other things suck, and so you've got to mix and match.
Sure.
There's no single.
There's so many other things too.
Is there any free knowledge base out there since Google retired their knowledge base last week?
There's so much of material available. I think it depends on what you're looking for, whether it's just a translation related. There's so many blogs and papers and corpora available for translation alone. There are free models available, translation models available by different universities.
Not translation, just say part of speech tagging. Where do I learn that Harvey is hurricane or might also be massive? Where do I learn this?
See, Harvey is a hurricane or not, I think that depends upon what type of data set you already used. And I don't know whether people are updating the data set as such. Stanford actually, I think Greg was mentioning too. Yeah, Stanford NLP actually data set I think is maybe more relevant. But I don't know. I don't do POS tagging anymore. All my NLP research is all at deep networks, so I don't use any of these things myself. So, but I think if you really want to get introduced to NLP and stuff, I think this would be a good study. Let me.
So you mentioned you're working with the healthcare space, and so I was wondering, like, when you're going through, or first of all, like, what kind of data are you looking at? Is it like claims data, like EMR data, or like are you going through forums from different diseases, or and like what kind of like problems come up in that kind of text?
Yeah. So I'm right now focusing on the cancer research, where I think I'm looking at the narrative part and the image part. We have the scans of tumors, and then also you actually have text of the patient conversation with the doctors, and trying to combine these two to see if I can make any sense, define an NLP model to make accurate predictions about what's happening with the patient. Let's say if my question is, will the patient's tumor grow double in the next 2 months or not? If that's a question I want to answer, I think I want to create an NLP model where I actually can look at the scan, look at the data, and then make a prediction. So the multiple questions can be, but my focus area is currently cancer research, and there's a lot of investments happening in cancer research too. Yeah.
Okay.
Yeah, if you want to start a company, that's a good idea also to go into that because VCs can give more money there.
My question was on how would you inculcate both the numerical features and text features if you're doing say for the medical applications, say you have the customer reviews or the conditions about the patients, and also you have few statistical reports about the patients as well on the same. How do you combine both of them to create a model? Because combining word to vectors would give you a sparse matrix, and just using a hash maps or something to put both of them together wouldn't give a lot to the model.
Yeah. So you're actually combining multiple things in it, but in the healthcare area, if you have unstructured data and then structured data, so for a lot of companies, what the basic algorithm or approach that they're doing is convert the unstructured data into a structured data. So try to do some translation. So if the doctor says the calcium content in the blood is low, calcium content is acceptable, calcium content is greater than 10. All of these may be the same thing. So if you have enough rules and using the tagging and all of the extraction and other stuff, and then you identify what the message is and then update your structured data. And then it becomes just a basic database and then you run on it. So, but that's different from the neural networks because they're, right now, half the problem is in the healthcare, especially if using NLP, converting the unstructured to the structured. after you've done the structured data, then you actually can do a deep neural networks to run models on trying to figure out, make some sense out of these data. Now, the word to vec, etc., I have not seen being used as much because the unstructured reports, the narrative reports are being converted into structured report. Because typically the doctor says the patient has high blood pressure. Well, and the next, some other doctor says the patient has blood pressure of 200. If both are same, then let's say high blood pressure may be equal to I don't know, between 120 and 200. So you update that in the record, and then now you actually have all the patient records converted from the unstructured to the structured, and then you run the basic analytics. There it's not deep networks especially. Deep networks comes in NLP with more on the translation, summarization, abstraction. So healthcare is slightly different. Yeah. But if you are using summarization or question answering for documentation available in a tech company, then you can do deep networks to actually do NLP and then get answers for questions or summarization, all that stuff.
Do you have any recommendation for particularly for finance industry, like NLP?
There's lots of information available online. I don't have it myself, but I've written blogs on pure NLP tech stuff. If you go to my LinkedIn, you can. My LinkedIn thing is available in the here. Financial, I've not worked on. That's another huge area. I've seen lots of companies working on, especially hedge funds, helping hedge funds to make predictions. But they're not using as much deep networks versus using some of the machine learning models, including XGBoost and some of the SVMs and those things they're using, which is not really deep networks. Yes, sir.
Are POS-based tagging approaches, are they kind of old hat now? Are they becoming obsolete? Because deeper, if you have tons of data, deeper and read it, but if you don't, if you have sparse data, is POS still repetitive? Or like ensemble?
The purpose of POS is once you do the tagging of parts, the speech parts in the sentence, you would do a sentence chunking or a segment chunking to identify what are the subjects and the objects and the verbs and negations and those things, and then you actually make a tree, a graph out of it to eventually make sense. I think I gave an example here. The second pronoun resolution. The thieves stole the paintings, they were subsequently sold. Using the POS tagging, you can actually upgrade the text where the thieves stole the paintings, the thieves were the paintings were subsequently sold. So you can update by using POS tagging. One of the objective is to actually upgrade the text, and then the sentence, the second sentence, they were subsequently sold, can be written as paintings were subsequently sold. Now this sentence alone will make sense, and you can extract that and you can use that to make your question answering or summarization, whatever it is you're trying to make sense. So for that sense, POS becomes a stepping stone. Healthcare is one segment I think I've seen maximum usage for POS tagging and such tagging, where they're trying to make sense out of the unstructured reports. But once they convert the unstructured into a structured, POS is no more useful. They just do other analytics, basic data analytics, or deep learning.
All the corpus examples are complete grammatically perfect English sentences, but if you look on social media, you've got emojis, you've got hand symbols, you've got like mythology works with their, essentially unstructured text. And any POS tagger is going to be probabilistic, it's not going to be crisp and exact. And nobody's going to take enumerators to put down 10,000 figures. How do you deal with those?
Yeah, so those are all good problems. Actually, like I said, nobody pays. Actually, there are some companies which are hiring third-party companies where they're actually doing human tagging. That's one. I've seen some companies actually creating textual conversions of emojis, and you have multiple tags. Like, say, for example, a textual tags for emojis. They're using that and then replace the emojis and then reconstruct the sentence.
You can do a semi-supervised learning iterative approach. Label some stuff manually, store the remainder.
But yeah, my point is it's not an exact science, it's probabilistic. And the more degraded the text, the more probabilistic it becomes.
Sure.
Especially for people who don't use capitals and shit.
Yeah, that's a problem. Yeah, I don't have a solution for that. Yeah, I think people are trying to figure out. That's what sentiment analysis. I think even the example I showed and also I talked about later on. Sentiment analysis I think works. I think 95% maybe accurately, or maybe 90%, 100%. I think it's not. People I think are no more talking about just the sentiment analysis for the entire tweet, and then talking about, okay, instead of just talking about the iPhone, can you tell me which feature you like most and which feature you don't like? Is it the screen and the speed and the look and the feel or whatever? So now becomes an extracting. So people have moved on to
That's an information extraction.
that information. How you could do? Yeah.
So what do the chatbots use for customer service kind of application?
So there's one of the question answering method in the NLP, because you train a model, it actually does language modeling and also does goes and picks up which passage, where the passage is, and what the right answer is for that. So there's multiple things within NLP you use, but I think chatbot is one absolute useful implementation of NLP. Predominantly question answering. Also, if you look at the question answering, that sounds very question answering, but what it means is in the background, it has to know, it has to understand what you're asking, and then identify what where to look for the answer, and then once you know where to look for, then identifying and extracting the answer. So it is a combination of summarization, question answering, sometimes even translation. Chatbots are using translation also. Okay, thank you guys. Thank you very much.